So I'd like to start this out with giving you some background for myself so you know where I'm coming from. Before I was with UOSH, I spent about 10 years doing inspections for commercial insurance underwriters. They'd send us out, we were their eyes and ears. And that was kind of fun. You saw all kinds of companies and businesses, and we worked for a company that worked for all different insurance companies. So sometimes you saw this one place like several times, and they still had the same problems. But anyway, that was kind of a fun job. Then I spent 4 years at State History, which was even more fun, hanging out with the archaeologists. And then I came over to UOSH, Utah Occupational Safety and Health. That's what UOSH stands for. And I've been in UOSH since 2000. So I spent 8 years as a compliance officer, and the last 10 years I've spent as a consultant. And the reason that I switched from compliance to consultation is that I got really tired of showing up after the person's died, their arms chopped off, their fingers are gone, whatever. They're in the hospital trying to recover from some just awful accident. The compliance side, they're the ones that end up looking at all serious injury and death accidents in Utah. And there are a lot of those. We have fewer deaths, thankfully, but many, many serious accidents happen in Utah every year. And the compliance side writes citations. So you show up to the employers, all their employees are, like post-traumatic stress syndrome because they just watched this really traumatic accident and the blood all over and blah, 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 blah. And there's maybe a dead person and, they're trying to recover from that. And then you hand them a citation. Here, this is going to cost you $10,000 or $15,000 because you did this wrong. And I think that that's not the best way to help people. So I came over to consultation. Consultation, most people don't even know exists. We are a free, confidential service available to any employer in Utah. All you got to do is ask. We do not just show up like we did when we were compliance officers, and all of us in consultation used to be a compliance officer. You have to ask us to come in, and you have to agree that if we find a serious hazard, that you will fix it, or we can turn you over to compliance. So in my almost 18 years in UOSH, the office, that's happened one time that I know of, where we turned an employer over to compliance because they didn't fix something we found. So it's rare, extremely rare, because most employers that come and ask for help with consultation want help. They want to fix their hazards. They want their employees to work in a safe and healthy workplace. So one of the things I like to point out to everybody when I'm training them, because most people don't know this, can any of you guys tell me what is the difference between OSHA and UOSH?
Utah. It's a Utah thing.
Yeah, UOSH is Utah. I only have jurisdiction in Utah. I can't go to Nevada or Arizona and talk to somebody about safety and health stuff. I only have jurisdiction here in Utah. Okay, so what is OSHA? Does anybody know what OSHA, that acronym, stands for? Occupational.
Safety.
Safety.
Hazard.
Health. Safety and health. Administration. So, Occupational Safety and Health Administration, that is a federal government agency under the Department of Labor. So, OSHA came around in 1970. The thing about it is, many states, including Utah, we had an OSHA-like program sometime back in the 50s. I don't know exactly when it started in Utah, but I know that it went back at least to the 50s. Anyway, Utah and many other states around the country had their own OSHA program, kind of like OSHA. There was a variation on how strict they were, a big variation. OSHA came around and said, we need to standardize this across the country because we can't have companies moving from one state to the next saying, well, their OSHA-like rules are more stringent than that OSHA-like rule. And so they basically put in what is the minimum required standard for all employers to adhere to. There were actually some states that had no OSHA-like program at all. Employers could go in there and abuse their employees easily. Oh, what's that employee? There's another one out there that can just replace them. And that's their attitude that they had. Anyway, so when OSHA came around in 1970, many states applied and were granted what we call a state plan status. About half the United States and territories now are state plans. Utah's one of them. Most of the western United States are state plans, by the way. Utah has 2 federal states that border us, Colorado and Idaho. Wyoming's a state plan, Arizona's a state plan, Nevada's a state plan. The whole West Coast is a state plan. However, Idaho and Colorado are federal states, so they're under OSHA. OSHA does not come here and investigate anything unless it's at a federal employer like the post office. If they have an accident at the post office, UOSH doesn't investigate it, federal OSHA does. Okay, this is important to you guys, and here's why. In a federal state like Colorado, if I'm a local government employee like you guys are, and that means you're an employee of a subdivision of state government. Your authority, the county's authority, is a subdivision of the state's authority. It's under the state. So if you're one of those employees, so counties, cities, special improvement districts, school districts, any local government employee you can think of, in a federal state, you have no coverage or recourse under OSHA. OSHA does not apply to you. So your compatriots in the counties over in Colorado, they have nobody saying to the county employers, you got to treat your people well, and you have to comply with this minimum amount of safety and health stuff. In a federal state, there is no such thing. There are some federal states that have some voluntary programs, but it's voluntary. And so that basically means that they can or they don't have to. In state plan states, the state plan has jurisdiction over all local government employees. We enforce OSHA standards on everybody in that category. So if you have a problem with your employer, you can come complain to UOSH, and we will do something. We'll come out and investigate it. So I think that's the most important reason why you want to be in a state plan state, because you have recourse if somebody's mistreating you at work in that way for safety and health. In federal OSHA states, they don't have that recourse. And I think it's reflected when you go to Bureau of Labor Statistics and you look at how many people get killed in public sector, how many people get injured in public sector across the country. The statistics are really high for that group, higher than many construction trades, which are considered to be the highest private type of work that you're likely to get injured or killed from. The statistics for public sector are very high, and that's even if you take out the firefighters and the policemen. So it's kind of surprising, but I think one of the reasons that it's that way is half the United States has no OSHA standards applied to those people. So anyway, my soapbox. In Utah, how many people are we talking about for public sector? Anybody want to guess what percentage of the state that is?
Maybe 30?
Of all the people that work in Utah, 16% are public sector employees of some sort of public sector. So that's actually, a pretty good chunk of people. And I think it's important that we take care of our public employers and employees, because we do occasionally kill them off. We had 2 fatalities in public employer in 2016 and 1 fatality in 2017. So occasionally we do have fatalities that way, which is not good. Anyway, and that's why the compliance side of the office right now has what they call a local emphasis program. They're actually looking at all public employers in the state in cities that are over 1,000 people population. So you may have a compliance officer walk up to your door and say, hey, I'm here with compliance, I'm here to look at everything. That's a local emphasis program that compliance is running right now, UOSH compliance. So just, you might see them. Anyway. All right, so one of the things we do as a state plan is, rather than rewriting the book, all these OSHA standards, what a lot of work, why waste the time to do that? So what we've done is we adopted all of the federal OSHA standards. So you can actually go to OSHA.gov, that's federal OSHA, look on that website, and virtually everything on that website applies to us. Not all things, there are a couple of things that don't, but most of the stuff on there does. This is one of federal OSHA standards, the Hazard Communication Standard. We adopted it. So Utah adopted it in November 25th of 2012. We have 6 months after federal OSHA comes up with a standard or revises a standard to adopt it as a state plan. So that's how come the difference in when it was put in by federal OSHA and when Utah adopted it as UOSH. So this standard was actually an update of a pre-existing standard. The pre-existing standard was a hazard communication standard. We call this one Global Harmonization Standard, but we also call it HAZCOM. Same thing. So they were trying to update the old hazard communication standard in a couple of ways. The reason they call it Global Harmonization Standard, you've heard of our economies are all going global. In other words, what we do here in the United States affects other countries, and what they do affects us in the marketplace. This certainly happened with chemicals. So before this update in the standard, you could have a chemical that was called something here in the United States, and it was judged to be this level of hazard in the United States. You'd go to another country, it was called something different, and their idea of what's hazardous is different. So we might call it hazardous, and they don't. So they're not going to treat it like a hazardous chemical. And that was from one country to the next, the same, all the way across. You had all these different definitions of what is hazardous. You also called it some different chemicals. So I could call up somebody in another country and, well, I'm talking about this chemical. What are you talking about? And there was miscommunication going on and misunderstanding going on. So this standard was called globally harmonized because it actually was put together by the United Nations with OSHA as the chair, and they were trying to get everybody on the same page, talking about the same stuff. And so I think that was a positive with this idea. Another thing they were trying to do, in the United States, the old standard in the 1980s was called the right to know. This one, they're hoping people have a better understanding. Okay, I know about these chemicals, so what? What does it mean for me? This is the idea of understanding what that means for you. So one of the other issues with everybody not being on the same page, you probably have encountered this sometime in your life. Federal government agencies that don't agree on something. You ever encountered that? If you're in any kind of building code business, you probably have. So 3 specific agencies, US DOT, EPA, and OSHA. I've had employers say, well, DOT tells me I got to do this, and EPA says I have to do this, and then you guys come along, OSHA, and tell me I got to do this, and they're 3 different things, and you don't agree what we're supposed to do. So this was an attempt to get these 3 agencies to also agree on chemicals and how you handle them and what is considered hazardous and all of that kind of thing. So that's another reason why we call it global harmonization, is we're trying to get everybody to be on the same page and agree. So this particular standard got rolled in, even though it was adopted in 2012 and 2013. It had an existing standard, and this was the update of the existing standard. So federal OSHA kind of rolled it in at different times. So I'm here to tell you, none of these dates actually happened. Everybody was supposed to be trained on what this new standard says in 2013. That didn't happen. Everybody wasn't trained. A lot of people were, but not everybody. 2015, the manufacturers were supposed to have all their safety data sheets instead of MSDSs. That didn't happen. In fact, we're still working on that. 2015 might have happened. Distributors that had stocks of old chemicals had until December 1st, 2015 to get rid of the old chemicals with the old labeling. And that mostly happened. Then 2016 came along, and everything's supposed to be updated, all the training's supposed to be done, all the chemical manufacturers are supposed to have their part of it done. Mostly that happened, but we still come across manufacturers that are giving everybody MSDSs. So if you keep getting that from somebody for a chemical you have in your workplace, just know, keep asking. Eventually they'll get it updated, and I'm thinking maybe eventually federal OSHA will do something to them if they don't. We as a state really don't have a lot of leverage for that kind of thing. And actually federal OSHA doesn't have a lot of leverage in it either. So we're hoping, especially if it's in a manufacturer that's in China, for instance. It's really hard to enforce U.S. laws on China manufacturers. About the only thing we can do is basically block the product from coming into the country if it doesn't comply with this standard. And I know they've done that with some things. So anyway, just keep working on it. We'll eventually all get up to speed on this thing. So what we're doing today is making sure that you guys know what this is talking about and how it's important to your life. Okay, let's see, we talked about that already. So, you all know that it's no longer MSDS, right? Remember what MSDS was? Material Safety Data Sheet. That term is no longer used. Now it's SDS, Safety Data Sheet. Why did we shorten it? I don't know. I haven't found a good answer. The one answer I did get was, well, MSDS is also an acronym used in the medical community, and we didn't want to confuse everybody with that one. And I'm like, you know, if you waste your time trying to not step on other people's toes with acronyms, it's a battle you're going to lose, because if you've ever been in any other industry, there's acronyms that are the same, mean this thing over here and mean something totally different. But anyway, that's the answer I got. One of the things that this standard brings out is it assigns specific meaning to these two words, danger and warning. If you see something that says danger on it, on the label, that means it's pretty hazardous. If it just says warning, that's less hazardous. If it doesn't have either of these on the label, then it's less hazardous than that. Also, we have these pictograms. They're called diamond on point pictograms. They have a red border. If you don't see one of those on the label, it's not because it's just missing. It's because that particular material is not hazardous enough that it's required to have a pictogram on it. If you see a pictogram on a label, that means there is some hazard to this stuff, enough to require that pictogram. So pay attention to those things. They mean something. And we'll talk about that later. Also, there are some previous to this standard, unrecognized hazards that they didn't categorize. This standard categorized those. We're going to talk about that later. So, like I said, we're replacing all the MSDSs with SDSs. And we're doing the training right now. So the poor manufacturers, the lion's share of this went on to them, and it's taken them years to get this figured out. Lots of money and lots of time. So one of the things that used to really irritate me about MSDSs, if you'd ask an employer, I need an MSDS for this particular material, you might get one page that said almost nothing, no good information, or you might get 25 or 30 pages, a whole book of something, very technical, fine print. If I have an emergency and I'm an employee at an employer's place of business, and I need to find in that 25 or 30 pages the information about what do I do with first aid if a person's been exposed to this stuff, and I have to read through 25 or 30 pages of fine print to find it, is that a good way to go? Who's got the time to sit down and read that? So one of the problems with the old MSDS system, those things were written by quite often two different groups. The first group was the lawyers, and they would write these things because they don't want to be sued by anybody. So they would make something that's actually not very hazardous sound like it was going to kill you in a breath. And then, if you did use that material and you got exposed to it, you couldn't sue them for, whatever, because, after all, right here in the fine print, it told you, blah, blah, blah. Okay, so that group was really good at writing MSDSs, and a lot of that information they put in there is totally useless. Then there's the other group. They're the salesmen. They are trying to sell this chemical to employers. And so, do they want to make this stuff sound bad? If they make it sound bad, do you think they're likely to have an easy time of selling it? So they would write the MSDS to make it look like this is, oh, it's not that bad. It's not a bad chemical. Just, don't worry about that. No, anyway, so you have the two extremes. Which do you believe? And that was one of the problems with the old MSDSs. Also, there was no format required. Some of them are really hard to read, and you couldn't find the information you really needed in a hurry. So this new system requires a certain format, and it requires the manufacturers to compare their product with established definitions of what's hazardous, and fit it into those established definitions and rate it so that we have an idea how hazardous is hazardous. So here is how the standard is organized in the actual OSHA book. Most of you will never have to read these, but I tell you about them because that's where you can find them if you want to. So all of these appendices are mandatory. In other words, we enforce them as part of the law. Many appendices in the OSHA standards are not mandatory, they're advisory. So we are really not used to citing appendices when we write citations. Anyway, this is how it works. Appendix A is health hazards. It gives you what the criteria are for health hazards. Appendix B are physical hazard criteria. Appendix C, what do I have to put on a label? Tells you in Appendix C. Appendix D, what do I have to put into a safety data sheet and what order? And that's where it tells you what order. Appendix E, definition of what is trade secret. That hasn't changed from the last standard. And then Appendix F, guides for hazard classifications having to do with carcinogens, which are cancer causing. And this one is non-mandatory. It's like guidance. Okay, so there's new definitions in these, and OSHA has very well-defined things in both the label and the safety data sheet for these. So you have to now have a hazard classification and then a hazard category. There's a new category, or classification actually, hazard not otherwise classified. That's HNOC. There are some hazards out there they haven't really figured out a good category for yet, and that's what would go in there. Then you have things that are called hazard statements on the labels and in the safety data sheets, and what you have to put on the labels is very specific. And whether you need a pictogram or not, that's really specific. You also may need a precautionary statement and a product identifier. So one of these categories they've decided to put in as an official category is pyrophoric gases. Anybody have an idea what that means? What is a pyrophoric gas?
Pyro is fire.
Pyro's fire. Pyrophoric is actually Latin. Pyro is fire. Phoric means self-starting. So it starts itself on fire. And I can't think of a pyrophoric gas off the top of my head, but I'm sure there are some since they've made a category for it. There are pyrophoric liquids and there's also pyrophoric solids. So this is a good time to point out, if you're going to understand anything about chemistry, and this is chemistry, because the way chemicals work with us is chemistry, you have to understand the chemists all got together and thought, you know, we need a baseline, we need a 0 point. Because chemicals will act differently at different pressures and different temperatures. So where is our baseline? And so what they did is they named the baseline as normal temperature and pressure. You guys ever heard that term before? If you had chemistry at all, that's one of the first things they teach you. What is normal temperature and pressure, or NTP? So we're not normal in Utah. No place in Utah is normal.
Hi, Diane.
So, in case you didn't know that already, but where they decided normal was is sea level at 70 degrees Fahrenheit. So, if I'm at sea level, I have a certain amount of the atmosphere pressing down on me, so I'm going to have a certain kind of pressure. And 70 degrees Fahrenheit was just a random number that they chose.
I'm not normal at the beach either.
Yeah.
Right?
So as you go up in altitude, the pressure changes. It reduces. As you go higher, the pressure reduces because you have less of the Earth's atmosphere pressing down on you. If I'm on a mountain, I've only got this much. If I'm at sea level, I've got this much. So if I'm in Death Valley, which is actually below sea level, I have more than normal temperature and pressure. And that's what I mean by they had to draw a baseline 0 somewhere, and that's where they chose to do it, was sea level, because most continents have the same sea level. And 70 degrees, I don't know where they got that, but that must be an average of something. Anyway, so normal temperature and pressure is what they're comparing all these chemicals to. What's it going to act like at normal temperature and pressure? So keep that in mind. If you raise the temperature, most chemicals will do whatever it is they do more energetically. If you lower the pressure, or excuse me, temperature, most chemicals are going to do it less energetically. If you raise the pressure, many chemicals will change form. You know, there's 3 forms. There's gas, there's liquids, and there's solids. If I up the pressure on a gas, it's going to change to a liquid. So that's what we call liquefied gases, like LPG, liquefied petroleum gas. I've pushed pressure on it, and now it's a liquid. If I let the pressure off, it's going to go to a gas again. So we haul stuff around all the time in pressurized tanks, like chlorine, for instance, that if I let it out of that pressurized thing, it was a liquid when it came out, but it'll evaporate into a gas really quick. So the 3 states of matter are solid, liquid, and gas, and then there's normal temperature and pressure. You up the temperature or the pressure, all of those things are going to act differently. So for instance, if I boil water at whatever temperature it is at sea level, what happens when I get up on top of the mountain and try to boil water? What does that do to the temperature it boils at? I think water boils at sea level at, what is it, 212 or something? 212 degrees. If I go up on a mountain and boil water, it takes less energy to boil water. The temperature that it'll boil off at is lower. And it's because there's less pressure pushing down on the water at a place like a mountaintop than there is at sea level. So it boils at a lower temperature. Anyway, that's an example of how temperature and pressure can affect any chemical. There's another word in here I want to point out what it is. Simple asphyxiant. What is that? This is a gas, by the way.
You breathe in.
Something you breathe in. Reason we call it a simple asphyxiant, it's not a poison gas. So things we say is a poison to us, it's interacting with our body somehow and causing damage. Simple asphyxiants are not poisonous. It's a gas that's not poisonous to us. So a simple asphyxiant, for instance, we have a waste gas we breathe out. Do you guys know what that is? Carbon dioxide. Carbon dioxide is a simple asphyxiant to us. If you had this room filled with nothing but carbon dioxide, we'd all be dead. It's because there's no oxygen to breathe. Another thing that's a simple asphyxiant that actually makes up most of this volume of air that we're breathing right now is nitrogen. We breathe in and out all the time, every day, and it doesn't do anything to us, just takes up space. We can't use it. Our bodies don't process it. It doesn't interact with our cells, really. It's just a simple asphyxiant. If you have nothing but nitrogen to breathe, you're going to die because your body needs oxygen. So, while we're talking about oxygen, how much of this space that we're breathing, what percentage of this is oxygen? OSHA actually has a range. What's the breathable range that you should be in all the time? Our lowest is 19.5% oxygen. If it's any lower than that, you're going to have problems. They may not be major problems. It might take a while for them to catch up with you, but you'll have problems if it's lower than 19.5% oxygen. We have an upper range of 23%. So if it's oxygen more than that, OSHA says you shouldn't be working in it. Why do we have an upper range? You can go to the hospital and they'll give you pure oxygen and you breathe it just fine. Why does OSHA say you shouldn't be working in more than 23% oxygen? This all has to do with fire. Okay, if I have a fire triangle, you know, a fire triangle, what is it made of? What's in the fire triangle? You have to have a fuel. You got to have something to burn. Then, I got to have oxygen. And what's left? What's this third thing? Somebody said ignition. Okay, you're kind of right, only we talk about it as heat. I can actually heat anything that will burn in this world up to a certain temperature, and it will on its own be on fire because it starts interacting with the oxygen in the air. I don't need a flame, I don't need a spark. I could heat everything in this room to a point where it would automatically go on fire, and what we call that, if you're in the fire service, is flashover. That's what you've done. You've heated the whole room. Maybe I've got a fire going on in the room downstairs, but nothing up here is on fire, but that heat is coming through from downstairs. I'm heating the whole room up. There will be a point where the whole room's going to be on fire all by itself. So in a fire, you have to have those three things. You got to have fuel, you got to have oxygen, and you have to have heat. So the reason OSHA limits how much oxygen you should be working in is that we don't want to enhance the one side of the fire triangle, oxygen. If you're in an enriched oxygen atmosphere, things that you think would burn in a normal way burn really much more aggressively. So if you have a candle and you put it in an oxygen enriched atmosphere, that candle will not only burn the wick, it'll start burning all the wax and anything else that can burn. So we don't want to enrich our oxygen in our workplace because we don't want people to burn up. So that's why OSHA has that upper limit. Normal oxygen in the air is around 21%. It's actually 20.7 or 8. We round it up to 21. So if only about 1/5 of this air is breathable oxygen, what's left? What's the rest of it? I just told you one of the big components.
Nitrogen.
Nitrogen. The majority of what's left is nitrogen. Then there's the carbon dioxide that you and I are sitting here breathing out. And then there's a bunch of trace gases that are also in there. But the majority of it is nitrogen and oxygen. So that's important to understand as we go forward. Okay. So we already talked about these two. This combustible dust thing, OSH has been trying to write a combustible dust standard for more than 10 years, and they still don't have it. Federal OSH is really slow at writing standards. Sometimes it takes them. The combustible dust standard's been working on for at least 12 years that I know of, and we still don't have one. What's the big deal about combustible dusts? Why are they dangerous?
Because they burn.
Yeah. So if we have our fire triangle, what part of it is a combustible dust?
The material of the...
It's the fuel.
Fuel, yeah.
Okay, it's the fuel. And here's why dusts are so much more dangerous than just a normal fuel. If I have a big rock of coal, big massive rock of coal, can I light that on fire with one match? It's combustible, but I'm not going to get the whole thing on fire with one match. And the reason why is that it has very little surface area compared to its mass. And in order to get that whole thing to the point where it could burn, I've got to heat it up. Because remember, my triangle, heat. I need fuel, I need heat, I need oxygen. Well, I've only got a small surface area on that. Oxygen can't get to the stuff in the middle. And it's a big, massive rock. And so it's got a lot of inertia as far as heat. It would take a lot of energy to heat that up to the point where it would be on fire. Now, if I take that same big rock of coal and I grind it up into little teeny tiny pieces of coal dust, what have I done with our fire triangle? That one big massive...
You've added oxygen.
I've added oxygen to all the surface area of each of the little teeny tiny pieces of dust. I've made the surface area from this big rock exponentially larger, and I can get my oxygen to all of those sides of those little pieces of dust. And all I need is heat or an ignition source. Is it going to be a lot easier to heat up a little piece of dust than it is that big rock?
Yes.
Absolutely. You could have an explosion, because if I get it, in air, in a cloud, and then I add an ignition source to it, you could have an explosion. That's why dust is so dangerous. Can you think of anything else that might be a combustible dust that would be dangerous? What other things you might see in a workplace could be a combustible dust? So if I were home, what about the lint in my dryer screen? Could that be a combustible thing? Absolutely. Another thing, we have all these combustible dusts at home, by the way. Lots of them. Flour, powdered sugar. The thing that they use in the OSHA lab in Sandy, there's a guy in that lab that all he does is explode things every day. He gets samples of dust from OSHA compliance officers all over the country, and he puts them in his little sphere and gives it air and gives it an ignition source to see if it'll explode. And what he does, what he uses for tours that come around to demonstrate this, is the powder from mac and cheese, the cheese powder. That's very explosive. Some other things that are really explosive. I took a class from the National Fire Academy for firefighters, and it was the chemistry of hazardous materials, and one of the instructors was showing us about combustible dusts, And he walked us all outside. It was at a hotel near Park City. We were doing this class for 2 weeks. Anyway, he walked us all outside and said, now watch this. Don't show this to any teenager or talk about it. You know, I'm swearing you to secrecy with teenagers. He took a handful of coffee creamer and he threw it in the air, and then he put his lighter underneath the cloud. That was pretty impressive. It goes up with a big whoosh. Anyway, don't do that inside a building. If you want to try it, do it outside, because you'll end up either, you know, lighting the building on fire or starting the sprinklers if it's a sprinkler building. Anyway, combustible dusts are very dangerous, and that's why we have them in here as a category, even though OSHA can't seem to agree on what kind of standard we should have about them. Okay, one of the other things I wanted to point out about chemicals, they can be a safety hazard, and what we consider safety hazards is things like it's combustible, it's flammable, that kind of stuff. Or if it's a compressed gas cylinder and you knock the top of it off, it flies around the room like a rocket and hits people. That's a safety hazard. It could be a health hazard too. So if I have a compressed gas that is a poisonous gas, I could be hit by the tank as it's flying around the room, and I could also be poisoned by the gas. That's a health hazard. I could have things that are in both of these categories overlapping. I can have a chemical that's both a safety and a health hazard. So just be aware that you can't really comfortably divide them into the two camps, even though we'd love to. Sometimes they're in both. Be aware of both. Okay, so here's what the safety data sheet is supposed to look like. Number one, and this is done by order of what they voted on is most important to know first. So number one, what do you call this stuff? I've got to identify my stuff. It's got to have a name. I've got to have something that I can talk to other people about this material, this chemical. And if it has more than one name, I should put it in there. So here's an example. Do you guys know what is a common name for glacial acetic acid? Anybody heard of that?
Dry ice.
Nope.
Oh, I was guessing.
Good guess though. Anybody like dill pickles? What do we have in the dill pickle jar?
Vinegar.
Vinegar. That is glacial acetic acid. So if I have an SDS on glacial acetic acid, I better also put in there that it's known as vinegar. So another example of this, there was a small town in California a few years ago. They had this group come in and present to them about this really dangerous chemical, and they even had statistics to back it up. They said, okay, this chemical, it kills this many people every year, and it injures this many people every year. This is really dangerous. We shouldn't have this in the city. We should ban this chemical from our city. What chemical do you think they were talking about? Another name for it was dihydrogen monoxide. Anybody know what that is? H2O.
Water.
Water. Water. Dangerous. You know, people drown from water all the time. You can poison an infant with water if you feed them water and not formula. Water's dangerous. And that brings us to another issue that industrial hygienists use this. Actually, I think it was Paracelsus that first said this back in Greek or Roman times. The poison is in the dose. Everything in this world can be a poison to you. It really depends on how much did you get and exactly how did you get exposed to it. I can drink water and it does great things for me. It hydrates me and, you know, makes me feel good. However, I shouldn't breathe water. I'm not good at breathing water. It's really dangerous if I breathe water. I can die. And you probably shouldn't inject it straight into your veins. That might not be so good for you either. So it really depends on how you get it and how much you get, on whether it's a poison or not, because everything in this world could be a poison. So that's the other thing you have to keep in mind when you talk about chemicals and how much you get, because we are all chemical factories. There's this little thing in every one of your cells called a mitochondria that cell's chemical factory, and it pushes out new chemicals that help the cell do its function all day, every day. Without chemicals, we would die. We have to have chemicals in our lives, and we have to make the exchanges. So we take in oxygen, it goes to our body, and our chemical factories change it out, and we breathe out carbon dioxide as the waste gas. Plants love carbon dioxide. They breathe that in, and then they produce oxygen. So it's all, chemical manipulation. Okay, so number 2, hazards identification for my chemical. I need to tell people what are the hazards of this and what's, going to cause problems. Number 3, composition. What is my chemical made of? It's like putting down the recipe for a cake. I have so much flour and so much sugar and so much, whatever. They should be telling you what are the chemical components of this stuff. What percentage are they? Also in there you will see what we call a CAS number, Chemical Abstract Service. It's a number that's got digits, a dash, digits, a dash, and then some more digits. So 3 sets of digits with 2 dashes between them. If you stuck that number into Google, that is an international number for that particular chemical. So that number is assigned to that chemical internationally. It's called a CAS number. So you can actually look up any chemical and information on it. I've done this on the web by putting in the CAS number. So kind of a cool trick. Number 4, first aid measures. If I have somebody exposed to this chemical, what should I do? Induce vomiting? No. Should I give them milk? I don't know. Anyway, first aid measures, important. Number 5, if I have it on fire, what should I do with it? And sometimes water's not the best solution. Like any kind of metal fire, don't spray water on it. Bury it in sand, dry sand, not wet sand. Anyway, accidental releases. If I accidentally release this stuff, is it going to be a problem? And that really depends on what it is and how much you release. So for instance, if I have a 10,000 gallon tank of water that gets breached and I leak the whole 10,000 gallons out, is that going to be a hazmat response? Probably not, as long as it's just straight water. Now, if I have a pint-sized bottle of mercury and I drop it on the floor and it breaks, is that going to be a hazmat response? You better believe it. In fact, something like that happened outside of the junior high in Vernal. Some kid brought his dad's pint-sized bottle of mercury to school and dropped it right in front of the front door on the concrete sidewalk. That concrete is porous and it absorbed it, and kids walked through it and tracked it everywhere. They contaminated the whole building and most of the sidewalks and stuff in front. That was a state level hazmat incident. They ended up cutting all the concrete out, putting it in a hazardous waste thing and shipping it off to Energy Solutions. And they had to take up parts of the floor and the school. It was a mess. A mess.
So this might be a stupid question, but what does mercury do?
Yeah.
Why was it so?
Mercury kills brain cells. And it has a vapor. If it's at a higher temperature than just, a cool spring day, it will vaporize and you'll breathe it in. That's the fastest way to get it into one of your body systems and the fastest way to get it to your brain cells to kill them. Have you ever heard the term mad as a hatter? Like, Alice in Wonderland? That was a real name of a workplace poisoning injury. Hatters back in the 1800s and 1700s, where these big top hats were in vogue. They would make them out of the fur that was on a beaver pelt. So they'd get the beavers in the winter and they'd skin them and they'd tan them with the fur still on, and then they'd ship them to England or Europe or wherever, and they'd get that pelt and they'd shave off all the fur from the leather and they put it in this vat of mercury, and what they're doing is they're separating out the guard hairs, which are the long, long hairs on, you can see this on dogs or any other animal that grows a winter coat. You will see guard hairs, and then there's like a fluffy under hair, the stuff that floats in the air and gets on all your furniture and everything. Anyway, what they wanted was that fluffy under hair. So short of sitting there and picking out individually the guard hairs, because they didn't want that hair, what they did is they put it in a vat of mercury, and the guard hairs would float, and that fluffy undercoat stuff would sink. So it would separate those two kinds of fur. And the hatters would be stirring this, and it's on a burner so that it would heat it up, and that would make it more effective. So if you're standing over this vat of mercury and inhaling those fumes your whole work life, it didn't take long for their brain cells to die, and then they started acting really crazy and doing just weird, odd things, and they'd eventually die at a pretty young age because they were mercury poisoned. So mercury can be really bad to breathe in, and it can go through your skin too. It's absorbable through your skin. Especially for children, mercury is really bad. Adults has the same issue, but children are growing at a rapid rate, and so it can kill them fast. So, yeah, people say, yeah, when I was a kid, we used to play with the mercury from thermometers on my desk, and yeah, I remember doing that. But now we know what it does to people. So we learn. And that would definitely be a hazmat incident if you spilled that much mercury in a building or someplace like that.
So why did they ever put it in fillings? It's ridiculous.
Yeah, it is ridiculous, but they did.
Yeah.
I went in and had all my mercury fillings taken out, but they did. Silver mercury amalgams, when I was a kid, that's the kind of filling you got. And yeah, I probably lost some brain cells because of that. I remember the dentist, he'd squeeze it as much as he could and get as much of the mercury out, but dentists also were famous for having mercury poisoning symptoms, because that's what they did for a living. So anyway, okay, number 7, handling and storage. Where should I store this stuff? Should it store next to that other stuff? So if I have, for instance, oxygen and any kind of fuel gas, I shouldn't store them together, because the oxygen enhances how the fuel gas burns. So I should store them separately. They're not compatible. Exposure controls and personal protection. So this is the section you should be looking at before you ever handle anything. Do I need personal protection, PPE? Do any of you guys ever wear PPE for your job? So the things I'm talking about are gloves, dust mask respirators, face shields, safety glasses, steel-toed boots, some sort of lab coat, for instance. And by the way, the rubber exam gloves or latex or nitrile that you get, doctors use, those things are really good at keeping out large molecules like blood and viruses and bacteria and things like that. Good at that. But those kind of gloves, if you get into any of the hydrocarbons like gasoline, for instance, if you've ever tried dipping a nitrile glove in gasoline, or tried to do a stain on a piece of wood furniture, it's like they get stretchy and gooey and blah. Well, what's happening is that stuff is dissolving your glove. You don't want that, because then it won't protect you anymore. There is no such thing as a universal protectant for our personal protective equipment. You have to know what you're trying to protect yourself from and get the right PPE for that material, so that you don't end up dissolving your PPE in the middle of the project. That's happened. Once the PPE fails, you're exposed to whatever it was you were trying not to be exposed to. Okay, so number 9, physical and chemical properties. This is important because you need to be able to recognize what that stuff is. And here's the point where I tell people, do not use your 5 senses to identify an unknown chemical. Don't taste it. Don't smell it. You know, people do that all the time. The old cop shows, stick their finger in the, baggie of stuff. Oh yeah, that's cocaine, No, don't do that. If you have an unidentified substance, there's a really great thing you can download on your even cell phone and on your laptop. It's called WISER, W-I-S-E-R, Wireless Information System for Emergency Responders. You can give it the physical properties. Is it a solid, a liquid, a gas? What color is it? If you know what the odor is, like somebody's been exposed to it and tells you, well, it's got a fishy odor, you can put those things in WISER and it will narrow it down to what kind of chemical it could be. So that's a great way to figure it out. And sometimes it narrows it down in a really quick time. So anyway, know the physical chemical properties of what you're dealing with and don't use your 5 senses to figure it out. Number 10, stability and reactivity. Is this chemical stable or does it degrade over time? So an example of that would be picric acid. Picric acid is a liquid, but over time it forms crystals, and the crystals are actually explosive. All you got to do is move them. So people have been killed by unscrewing the lid on a jar that had picric acid crystals formed up around the top. Just jarring it that much exploded them. So for instance, nitroglycerin is another one. You see all those old movies with, they got this wagon and they're trying to keep from moving this little vial of stuff. It's usually nitroglycerin. They're trying not to move it because it's shock sensitive. Old dynamite is another one, shock sensitive. Age doesn't do good things to a lot of chemicals. It interacts with the oxygen in the air and other stuff, and it will make it unstable. So old chemicals are really not good.
Fireworks.
Firecrackers and fireworks can become unstable if they're old enough.
Okay, I'm going to go get them out of my trunk.
Age and heat are not good for those kind of things. Use them, and this is another thing. I love Costco, I really do. I live pretty close to Costco. You guys have any Costcos down here? People call Costco the $100 store because you go in there and you buy these very large quantities of stuff at real cheap prices. But do you really need 10 gallons of mustard? I mean, really? Are you going to use that much anytime soon? So this is the thing with chemicals. Don't overbuy because you got a good deal. Buy enough chemicals that you're going to use in the near future, and buy some more when you run out of that. Because chemicals a lot of times don't do well with age. So a good example, for instance, is, did you know your bleach at home will actually get less and less effective if you keep it over time? It's because the chlorine part of it evaporates out. So over time, the bleach doesn't work as well as it used to because the chlorine's evaporated out of it. So anyway, time and chemicals is not usually a good thing. Okay, so toxicological information. This one, if you see stuff like an LC50 or an LD50 on a chemical, what does that mean? So here's what that means. And actually they're essentially the same thing, just a different form. So LC50 is lethal concentration. That's something you can breathe in. So concentration is something that's airborne. LD is lethal dose. So something you ate, or I injected it, or I put it on my skin and it absorbed through my skin, so that's a dose. What they're doing is they're telling you, we had this test group of subjects that we made, and maybe they're 100 mice or 100 rats or 100 bunny rabbits or you know, a test group. And sometimes they have this information for people, by the way, because some of these chemicals are, you know, ancient and people have been exposed to them. So they know what the LD50 and LC50 are for these chemicals. Or they did things like World War II and they put cyanide gas in, you know, with a bunch of people. They know exactly what dose is going to kill half of the people. So I have my group of subjects. I'm going to up the dose until I get to the point where I've killed half this subject population. That's the LC or LD50. The reason they assigned it to that is that in any population you have outliers. You have people on this end, or subjects, who are very susceptible to this material and will react to it almost, you know, no dose at all. Then you have people on the other end who are very resistant and will react to it. You almost have to, you know, give them an elephant's dose to get them to die. So it makes a bell curve. So the really reactive people, and then the majority of them, and then the really resistant ones. So that's where we assign LC50. I've killed off half my subject group for LD or LC50. And that's where you will read in the toxicological information, what is the dose that killed off half the population? So that's going to tell you that this stuff might be kind of bad news if you see that kind of information. Okay, 12, 13, 14, and 15, I have asterisks next to them because OSHA does not enforce those. These are for EPA and DOT. So EPA wants to know the ecological information. If this stuff gets loose in our ecology, what is it going to do to the birds and the fishes and the insects and all those things? So disposal considerations. OSHA doesn't really care about that. We care about the people working in a disposal facility. As long as they have the right PPE on for what they're doing, okay, dispose away. EPA cares, what do you do with this stuff? Cradle to grave. And is it something that you can just throw the package in garbage and it goes to the landfill? Or is it something you have to put in an overpack jar and send off to Energy Solutions landfill? So that's what that says. The transportation information and the regulatory information is DOT. How much of this stuff can I carry on the road? Do I have to have a special package for it? So if I get in a crash with my stuff, will it get out? So for instance, if I'm gonna ship something like plutonium, if you've ever seen the container for plutonium, it's amazing. They subject that to all kinds of crashes and stuff, and it's not supposed to break, and it usually doesn't. So that's what DOT requires for chemicals. And then there's 16, other information, and usually in there it's something like, okay, I made this safety data sheet on this date. And you want to know that because as we go along as a society, we learn new things. If you've got a 20-year-old safety data sheet, probably there's other information on that material around. So maybe you ought to update that. Anyway, that's where that comes from. So hazards on chemicals in general, keep an idea that you don't want to get more of a chemical on you than you absolutely have to, no matter what it is. Because chemicals, they're not all bad, but we're back to the hazard is in the dose. If you don't need to bathe in it, don't bathe in it. So when I was going to Salt Lake Community College, I have a degree in environmental technology. One of the classes I had to take was basically how to learn to respond to hazmat incidents. So we're sitting there in our level A suit with an SCBA on and this entire encompassing suit. Look like, you know, the marshmallow guy. Anyway, they're very awkward, they're very hot, they're miserable to be in. But anyway, so the instructor in that class said, okay, so you got this PPE on for this stuff that we're going to clean up. That doesn't mean that you should go over there and kneel in the stuff. Don't get more of that stuff on your suit than you have to. Because the more you get on your suit, the more you're going to have to be decontaminated. And no decontamination is perfect. So if you don't have to get it on you, don't get it on you. That's just a good rule of thumb with chemicals anyway. I don't know if it's going to affect me, and I don't care. If I can keep from getting it on me, great. Because here's another little scary fact. They have estimated, and I've heard different numbers on this, but a good average that I've heard, that there are about 1,000 new chemicals that come on to the market every day.
Wow.
And many of them, we have no idea what they do when it interacts with a human. So an example of this, and you know, we're all guinea pigs in some form. An example of this, remember the whole thing over BPA? They made water bottles out of it. They made baby bottles out of it. They made drink, things out of it. They made milk jugs out of it. It was a type of plastic that was a thermoset plastic, and they thought it was going to work great. Well, they put it out there for all of us in the public, and we started using it, and then they found out there are some of the population that have bad reactions for BPA, this chemical, and so now you get all these labels on packaging and plastic bottles and stuff says BPA free. That was a chemical somebody came up with, and they didn't test it on anything. They thought it would work. Maybe the ingredients that went into it were not problems, but the way it was put into BPA became a problem. Another example that we had a big thing on with OSHA, any of you women go to the hair salon? So you go to the hair salon, and this isn't so much for Caucasian women, but especially women of color would go to the hair salon, and they didn't want the kinky, hair. And so they had this product called Brazilian Blowout. And what it did is it straightened people's hair. Now, I don't have that problem. My hair's straight anyway, so who cares? But people that go into the salon and they don't want kinky hair would get them to use this product on their hair. Well, you look at the SDS on the product, and there's nothing that's a problem. Okay, yeah, this all looks good, no problem. But you add heat in the form of a blow dryer, and this stuff produces formaldehyde. So the hair dryer people, in a salon, were being exposed to formaldehyde, which is highly poisonous to humans, because the material they had, you add heat to it, the way it decomposes in the heat was the chemicals it threw out was formaldehyde and a bunch of other things, probably water and some other things. But that's the thing, is they didn't realize when you add heat to this, it's going to produce formaldehyde. And that's the thing, we're all guinea pigs out there. And we can't possibly test all those products that are coming out all the time. So just be careful. Okay, so let's see. Okay, I need to go over these physical and health hazard categories because I want you to understand what they're talking about. So these are the categories out of Appendix A and Appendix B. We're going to go over these terms so you understand what I'm talking about. All right, so I'm doing them backwards. This is Appendix B because it's physical hazards. Most people actually relate better to physical hazards than the health hazards. Anyway, you'll notice the lower the number, the higher the hazard. Some of these categories have lots of categories. Some of them have one. And I don't know why they did that. They just did. So here we go. Everybody knows what an explosive is, right? Firecrackers, they go boom. Flammable gases. So I can think of a couple of them. Acetylene, natural gas, that's a flammable gas. Flammable aerosols. I'm not sure what the difference, well, a gas is a molecular thing. Aerosols is actually little droplets of water or a liquid. So your hairspray is an aerosol, for instance. Oxidizing gases. Those are things that have oxygen in them, that will interact with something that is combustible or flammable. So oxygen is an oxidizing gas. There are other gases that will act that way too, not just oxygen. Gases under pressure, and the reason these are in this category is not because they're poison or flammable or whatever, it's because they're under pressure. Any gas under pressure wants to get out. If you take a cylinder, compressed gas cylinder, and you knock off the very soft brass end of it, it will immediately be a missile, just like blowing up a balloon and letting it go. It goes like this all over the room. Only those things have punched holes in concrete block walls and concrete walls. They could certainly punch a hole in a person. So that's why they're in a physical hazard. Flammable liquids. Everybody's familiar with flammable liquids, right? Gasoline, for instance. But, you know, this is kind of a tricky thing about flammable liquids. What part of, I've had people tell me they could put out a match in gasoline. And yeah, actually, you probably could, given the right conditions. Don't do that, not a good idea. What part of gasoline actually burns? Is it the liquid?
Oxygen.
So if I have a thing of gasoline, it's that layer above it, the vapor part of it, that's what burns.
And that's where the oxygen is, right?
Yeah, and it mixes with oxygen and air. So, you know, all these videos on YouTube and wherever that show people lighting their car on fire at the gas station, it's not because of the cell phone. I'm here to tell you. A cell phone does not have moving parts. Can't be the cell phone. What it really is, you guys, and I do this too, when you get out of your car, you produce little teeny sparks of static electricity. During the daytime, you won't see them. At night, you might see them. But when you get out of your car, the first thing you should do is touch something metal, whether it's the outside of your car or the gas pump itself. What you're doing is you're grounding any static charge on you to something else. Then, get the gas pump going, pick up that nozzle, put it in your car, and you will notice there's this, you know, spiral thing around the hose. What that is it's a piece of wire that is grounding and bonding your car. It touches the metal filler of your car and bonds any static from your car back to the gas pump through that metal. Now, if I get back into my car while I'm filling it, I have the opportunity to create more static electricity on my, you know, seats and my hair and clothes, and because they're rubbing against each other. Then I get back out, and what's going to be around that filler? If I have an empty gas tank, is it really empty?
Gas.
It has a vapor stage of gas. So as I put gas in it, it's pushing that vapor out. So all the way around that side of my car is this big vapor cloud of gasoline, unless you're in California, where they capture that back into the hose that goes back into the pump. Have you ever seen those funky hoses they use in California? That's why. Because the EPA in California says, I don't want all this gasoline to be up into the atmosphere. It's because of EPA, not because it's a danger to you, that they recapture that. Anyway, in Utah, you're going to be standing in a cloud of gas, and if you have a spark on you because of static electricity, you could start the whole car on fire. So if you get in your car again and you get out, make sure you touch a metal part of your car when you get out again, before you touch the gas filler, because it's the statics that's going to kill you. Okay, flammable solids. There's an example of a flammable solid. You probably don't even know what it's like. Sodium metal is a solid, and it's kind of a chalky looking thing. They ship it around in water, because the minute it dries out, it starts interacting with the oxygen in the air, and it will go on fire all by itself. So sodium, unless you're a chemist, you're not likely to come across that. But anyway, that's an example of a flammable solid. Self-reactive chemical, I could put sodium metal in that too. All I got to do is dry it out. It starts on fire. Pyrophoric liquids, solids, and gases, same thing. They start themselves on fire, or need very little They might be a hot day would start it on fire. Self-heating chemicals. So have any of you ever bought those things from the store? You're going to go camping and you want warm hands, and so you buy those little things. That's a chemical reaction in there that you start when you bend it or whatever it is you do to it. And it combines a couple chemicals, and one of the results is heat. It produces heat. So they use one of those kind of things on me every time they want to take blood, because I have really tiny veins, and so they get one of those and they wiggle it and stick it on my veins where I'm going to take blood, and that's supposed to bring the vein to the surface so they can actually find it. Anyway, that is a self-heating chemical. Chemicals which in contact with water emit flammable gases. So the only one I can think of that fits this category is sodium azide. That's actually what runs your airbag in your car. If you get in a crash and it blows up in your face, sodium azide is what's causing that. But if you take sodium azide and you add water, what it does is it grabs onto the oxygen in the water and it releases those two hydrogens, and now you have hydrogen gas. So batteries are another thing that does that. The process of charging your battery will glom onto the oxygen in the water and release the hydrogen. So any battery charging areas should have a lot of ventilation, because you don't want that hydrogen gas collecting. Oxidizing liquids, or any liquid that acts like has oxygen in the molecule that will act on a fuel like oxygen. So here's a famous group of oxidizing liquids, organic peroxides. So if I have my hydrogen peroxide in my bathroom at home, is that going to hurt me? Is it going to go on fire? Because it's not a stable chemical usually. Should I run home and throw that away? No. Very dilute with water. So that stuff, unless you drink it, it might not do too well if you drink it. Or you soak a body part in it for a long time, might cause problems. It's not going to be an unstable chemical in that kind of dilute solution. But if it was pure peroxide, yes, it's an unstable thing, because peroxide means two oxygens in the molecule with a double bond, and that's very unstable. Easy to come apart. You've already got the oxygen in the molecule, and you usually have organic, anything that was alive once, there's the fuel. So in that molecule you have oxygen, you have fuel. What do you need to make a fire? What's left?
Heat.
Heat. So if you heat up an organic peroxide, you're going to have a fire. Things that are corrosive to metals. Can you think of anything that might be corrosive to metal?
Acid.
Acid, water. Yeah, the rust is the evidence of the corrosive. Just plain oxygen is also corrosive to metal. If there's humid air, for instance, you will have rust, because it's an oxygen consuming reaction. So we talked about combustible dusts already. So here's the health hazards. What does the word acute mean?
Severe.
Severe. Immediate. Immediately severe. That would be a good description for acute. So if something's acutely toxic, that's going to cause you problems right now. Skin corrosives or irritation. So what we're talking about in this category is something that's along the pH scale. You guys ever heard of the pH scale? It goes from 0 to 14. So 7 is right in the middle, and that's water. It's also, by the way, what your blood is. 7 is pretty neutral. You get off to one side or the other of the pH scale, and one side is acid and the other side's a base. The closer to the ends of those pH scales you get, the more corrosive it is. Both sides are corrosive. So if you are dealing with acids or bases, they're both going to essentially have the same issues with humans. We don't do well with really heavy acids and really heavy bases. However, we do actually tolerate acidic stuff better than we do basic stuff. I can drink lemon juice, and that's actually pretty darn acidic. I can drink glacial acetic acid, also known as vinegar. That's pretty acidic. I can't drink Drano. That's not good. And that's the basic side. So humans actually deal better, tomatoes are very acidic, with acids than they do with bases.